Hi, I'm Mr. Evans, and in today's video we're going to focus on speed, velocity, and acceleration. Now we're going to start by beginning our discussion with speed and velocity, mostly because both are very similar. However, you're going to find that we're going to spend very little time on speed and most of our time on velocity because that's what we'll use most of the time, both in class and in science. Okay, so speed is the change in distance over the change in time. And so this can be written a lot of different ways. So your change in distance can be x final minus x initial over time final minus time initial. Okay, but this can also be written as delta x over delta t. And you're going to see that I'm going to be using delta a lot more in this video, but just know that it means change in, and change in means final minus initial. Okay, and so let's do a real quick example here where if an object, so let's say we throw a ball, and that ball travels 10 meters in 4 seconds. Okay, and so we need to solve how fast it was thrown, and so it's speed. And so x final would be 10 meters, right? We threw it 10. X initial is going to be 0, right? It started with us. And then time is 4 seconds. Time started at 0, and it ended at 4. And so our equation is actually 10 over 4. And so its speed was 2.5 meters a second. And it's important you get used to that meters per second because that is the SI unit for speed and velocity. So velocity is very similar in that it's actually displacement over time, or change in displacement over change in time. And so all that really does, as far as we're concerned, is it adds direction to it. And by adding a direction to it, it makes it a vector and therefore more useful to us. And that is why in most scenarios we will be dealing with velocity and not speed, even though the equations may be similar. And so let's move on to a few examples here where we could solve for speed and velocity. And so in this scenario, what you're going to see is I've drawn a track in the top left-hand corner of our screen. And I don't know why, I just keep going back to tracks. But in the 100-meter race, you actually start at the 300-meter mark and you run to the 400-meter mark. And so why I like this example is it makes our displacement a little bit harder to solve for because you're not starting at 0. So in this scenario, our person ran from the 300-meter mark to the 400-meter mark in 11.6 seconds. It's a very realistic time in track. And so what I want to know is what was their average velocity. Okay, and so what we need to do is remember our equation, which again is delta x over delta t. And we need to remember that that is x final minus x initial over time final minus time initial. Okay, and so let's plug in what we know. So we're solving for velocity, and so what we know is he ends at the 400-meter mark. So our final distance was 400. However, did he run 400 meters? No. They started at the 300-meter mark. Okay? And our time was 11.6 seconds. And again, without being given any type of initial time, it's probably safe to assume that they started that stopwatch at 0 seconds. Otherwise, it'd be a really weird race. And so what we need to do is do the math. And so delta x is 100. Delta t is 11.6. And so our person's average velocity in this scenario was approximately 8.62 meters a second. So now we're going to move on to our last word, which was acceleration. So acceleration is the change in velocity of an object. So if an object is moving at a certain velocity, in order for it to accelerate, that would mean that it would have to speed up or slow down, resulting in a different velocity. Okay, so in this equation, acceleration is the change in velocity, which is Vf minus Vi, over the change in time again. So final time minus initial time. And again, that's just known as delta V over delta T. Change in time over change in velocity. Again, crucial. Final velocity needs to be first so you can show a positive versus negative acceleration. Okay, and so let's move on to a scenario here. And let's say we have a car driving down the road. And I'm going to draw a car, and it will be terrible because I cannot draw. And there's our terrible car. And our car is moving 25 miles per hour because it's, you know, cruising around in town. But then it jumps on the highway and it speeds up to 55 miles per hour, and it does so in 7 seconds. Okay, so we need to recognize each of our unknowns to solve for its acceleration. And in this case, its final velocity was 55 miles per hour. It went from 25 to 55, which means it's currently going 55, so our final velocity in this scenario is 55, minus initial velocity, which was 25, right? It started at 25 because we were in town, and this occurred over 7 seconds. So I could do 7 minus 0, or we could just do 7. So we do 55 minus 25 is 30 over 7, and so what we get is its acceleration was 4.3 meters per second squared. And what you want to know is meters per second squared, or meters per second is the SI unit for acceleration. What that means is this: it sped up 4.3 meters per second every second that it was speeding up. Now, to go ahead and get one more example in here, what you'll see is off to the left I drew a table, and what I want to know now is, you know, what was the acceleration from 2 seconds to 5 seconds? Okay, and this is a little bit trickier because we're not starting at 0 time, which is why I wanted to do this scenario. So we're starting at 2 seconds and going to 5 seconds. Now I haven't written units on here. Time, though, is in seconds, and velocity is in meters per second, and, you know, the normal SI unit, which will mean our acceleration is in normal SI units. And so what we need to do, and what I would start with, is let's write down our equation. And so we have Vf minus Vi over our final time minus initial time. Now, in this scenario, what is our final velocity? And so, you know, in time, you can only move forward in time. There is no going back in time, at least not yet. And in this scenario, our final time is 5 seconds, right? It's right down here. And so our Vf is 10, and our final time, our TF, is 5. Okay, and what about our initial? So when did we start this? And in this case, you know, my question was, what was our acceleration from 2 seconds to 5 seconds? So that means right here is our initial. And so our initial velocity is 18 meters per second, and our initial time was at 2 seconds. All right, and so let's go ahead and write this out, and we should have a -8 on top and a 3 on the bottom. Note, the bottom number should always be positive. You can't have a negative time. Similar to how I said you can't be negative far away from something in one of my previous videos, something can't take a negative amount of time. So in this scenario, we have -8 over 3, which you could be saying, hey, you know, negative, that seems kind of weird. And so first, let's go ahead and write this out. So you have negative 2.67 meters a second squared. And so what that negative means, which it is correct, you have a negative acceleration, which is the same as slowing down. And so that makes sense, right? If you look at it, and whatever this was, let's say it was a boat, you know, if your boat was going 18 meters per second, and 3 seconds later it's going 10 meters per second, would you say you've slowed down? Certainly, right? You've slowed down 8 meters per second over the span of 3 seconds, which is where we get these numbers, which is where we get this average. And so that means we slowed down approximately 2.67 meters per second every second. Thank you, and hopefully this helps you understand speed, velocity, and acceleration.